All right, everybody, I just want to review a little bit what we did with angular quantities today. So angular quantities. Let's just quickly remind ourselves of what we did. So over on the right, I have a circle here. It's a little dot moving around the circle. It's moving at an angular velocity omega, so it's rotating in this case, the counterclockwise direction. It's starting at theta initial, going to theta final. So theta represents the angle, the way it's moving, and omega is the rate of change of theta. And now this might be moving from theta initial to theta final at a constant angular velocity and therefore not accelerating. It could be accelerating uniformly, so it's speeding up or slowing down steadily, or it could even have some wonky angular acceleration, like it's getting faster in a non-uniform way. So given all that, the most general way to represent the relationships and the definitions between omega, theta, and alpha, the angular acceleration, are as follows. So first we have theta, which is just your function. Theta is some function of time, presumably, and that has units of radians. Now, omega, the angular velocity, which is how quickly the angle is changing by. It's sort of the speed of the angle, how fast the angle is changing, is just d theta dt, and that has units of radians per second. And then the rate of change of the angular speed, this is called the angular velocity. The rate of change of the angular velocity, so how that, whether it's speeding up, slowing down, how quickly it's doing that, d omega dt is alpha, the angular acceleration. Kind of like an A for acceleration, but angular. So d omega dt, and that is radians per second squared, and it's called the angular acceleration. Okay, so those are our three quantities. Theta in radians, which is just the angle, omega, the rate of change of the angle, which is the angular velocity, and alpha, the rate of change of omega, which is the angular speed. And these are directly analogous to position, velocity, and acceleration. So these points, if we go back on the circle, this point is moving with the velocity v initial. This point is moving with the velocity v final. They accelerate a in between. S is the distance that it travels, and so you can really think of this as a linear problem, but it's really helpful with rotation to have angular variables to describe the rotation. Okay, since we know S equals r theta, I'm going to write that over here. Well, I know ds dt is just my velocity, and that's going to be r d theta dt, but d theta dt is just omega. I know dv dt is my acceleration, and that's going to be equal to r d omega dt, but d omega dt is just my angular acceleration. And so I can go from my angular variables to my true linear variables and things like meters and meters per second squared simply by multiplying by the radius of the circle. And this is assuming that we're dealing with uniform circles. Okay, so using that, I can do something really cool. Now, I never said that, alpha, the angular acceleration, that could be a time-dependent quantity. Omega can be time-dependent. So really, we have theta as a function of time. We have omega as a function of time, which is d theta dt. And then we also have alpha as a function of time in its most general sense, is d omega dt. Remember, we could have the same thing with position, velocity, and acceleration, but if the acceleration was uniform, meaning that the speeding up or slowing down was happening steadily, we got the big three. Well, we can do the same thing. If alpha is constant, alpha is uniform, we can wind up deriving a version of the big three just for angular quantities. So let's remind ourselves of the big three, which was when A is uniform. So A uniform. I'm not going to write all five, just the big three. We had V final equals V initial plus AT. We had delta X equals V initial T plus 1/2 AT squared. And we had V final squared equals V initial squared plus 2A delta X. Now, if my alpha is uniform, all I need to do is replace all of my delta X's, which is like S, with r theta. S is like delta x, r delta theta. I can replace all my V's by R omega and all my A's by R alpha. And if I actually go through and do that, plug all of those in, I wind up with omega final equals omega initial plus alpha t. I wind up with delta theta instead of delta x is omega initial t plus 1/2 alpha t squared. And I wind up with omega final squared equals omega initial squared plus 2 alpha delta theta. And I can use these in the same way provided that my alpha is uniform. Same as when I can use the big three. Okay, so let's use them right now. Let's go over here to the next page and let's look at a problem from the slideshow. So we have a flywheel and you're given a bunch of information. So a flywheel, we'll just think of, we have a circle. Here's a circle, let me draw it. And that circle is rotating, let's say in some way. And it's rotating, a point on that circle is gonna go through 40 revolutions. And in the process of going through the 40 revolutions, it's gonna slow from an angular speed of 1.5 meters per radians per second to a stop. So let's actually write down what we know. We wanna know the angular, and we wanna figure out the angular acceleration and how long it takes to come to rest. So since I know the angular speed initially is 1.5 radians per second, and I'm going to call it didn't specify what direction it was going in. I'm going to assume it's going counterclockwise, and I'm going to call that positive. Angular speed is omega initial is equal to 1.5 radians per second. Omega final is 0. Now, I'm not totally told my delta theta. I'm told that it goes through 40 revolutions, but remember there's 2 pi radians per revolution. So times that by 40, I get 80 pi radians equal to my delta theta. So sometimes you'll have to figure out the delta theta if you're given it in terms of revolutions. Okay, what's the angular acceleration? Well, I don't know my time and I don't know my alpha. So that's going to make me use equation 3. So omega final squared equals omega initial squared plus 2 alpha times delta theta, which is 80 pi radians. And if I just solve that, I don't have my calculator, I get negative 2.25 radians squared over second squared divided by 160 pi radians. And that becomes whatever that is, negative 2.25 over 160 radians per second squared. And so that's my alpha. Now, notice my alpha is negative, my omegas are positive, so that's consistent with slowing down because when they're opposite, I slow down. Now, if I want to get how long it takes to come to rest, I just do omega final equals omega initial plus alpha t. Omega final is 0, omega initial is 1.5 radians per second, plus alpha, which I plug in for that, and I solve for t. So that's how you do these. They're not so bad. They're just like kinematics, but with rotational variables. We're going to take these and we're going to use them now in order to apply them to what happens when you have a net torque on a system and it actually begins to rotate. We're going to see that torques cause angular accelerations, and then we're going to be able to get those accelerations just like forces caused real accelerations. Once we had that acceleration, you could back up and figure out kinematics. You can back up and figure out how a wheel is going to rotate in response to a torque. And so that's what's coming next. All right, you guys, I will see you later. Hope this helps. Bye.